This lesson is an example of implementing the same simple algorithm 4 different ways. The only real difference among the implementations is where the variables are stored and how they are accessed. This is the function to be implemented. It's entirely an integer operation. It finds the largest common divisor of two numbers. Now it does so by looping as long as the value of x is not equal to 0. At the top of the loop, it tests the two integers to make sure that x is not smaller than y, and it swaps them if it needs to. Then x is divided by y, and the remainder of that division is used as the new value of x. That is, x becomes a result of x modulo y, so if y happens to be an even divisor of x, x will become 0, and y will be that divisor. This loop continues until x is finally 0, which means that y is the value of the greatest common divisor. If the two numbers are relatively prime, that is, they have no common divisors, the result is 1. There is more than one way to set this up in assembly language. This example puts the two values x and y into named memory locations and works with them there. Two reserve opcodes are used to declare locations in memory for the two 32-bit integers. The name of the function is declared as a global GCD mem. The arguments are passed from the C function by being placed on the stack. The MOV instruction is used to reach down into the stack below the return address and retrieve a copy of the arguments. In the preamble, the EBP register was set to the top of the stack, so even after a number of pushes and pops, access to the arguments remains exactly at the same offset. The loop label at the top of the loop comes right before the value of x is tested for being 0, and if it is, we're done. Then a test is made for size, and if necessary, the two numbers are swapped. It is necessary that x be larger of the two numbers. Next comes the modulo operation. First, the two values are moved into registers. Then comes a special instruction. This sets up the number in EAX for the division. All this instruction does is extend the sign of EAX through the EDX register. In other words, it sets the value of EDX to either all ones or all zeros, depending on the sign of EAX. This is a bit odd, but it's necessary for the division to work. The division operation then divides EAX by EBX, and the remainder is in EDX, which is the number that we want. Once the value of x becomes 0, the value of y is returned as being the greatest common divisor. The C compiler expects the return value in the EAX register. This is the C program that calls the function. The GCD function is called the same as any other function would be called. These printf statements display the two values passed to GCD mem and the result. Here's how it looks when you run it. This is the result of two calls to the function along with the values passed to them. But there is another way to keep the values in local storage. This is a method of storing the variables in a way that allows the function to be thread safe. This is the same algorithm. The only difference is where the local values of x and y are stored. This subtraction from the current stack pointer leaves unused space on the stack that can be used for local work storage. The first thing that happens is the argument values are copied into this new workspace. Then, throughout the function, the two values at the locations -4 and -8 from the EBP register are used for local storage. You can see how this function is thread safe because each invocation of it has its own workspace. This example has its own main line and runs just like the previous one did, but assembly language being what it is, there is yet another way. The arguments are pushed onto the stack when the function is called, so there is no need to copy them at all. This example uses them right where they are. Sure, their arguments are destroyed during the execution of the function, but so what? They're not used again for anything. This program does exactly the same thing as the others. There is one more. This one's my favorite. This one copies the values into registers and uses them there. The only time this version accesses RAM in any way is the initial copying of the arguments into the registers. The register EAX holds the value of X, and the EBX register holds the value of Y. This way, when the comparisons are made, it's done with the registers without loading any values. To swap the values of X and Y, it is only necessary to execute the exchange instruction, which swaps the values of two registers. And as you can see, the whole thing is much shorter because there is never a need to load values from memory or store them back. As a result, not only is it smaller implementing it this way causes it to run much faster. Now that's not so important with this algorithm because it's so simple, but something a bit more complicated that requires a few hundred iterations could benefit from this kind of implementation. It's harder to do for three reasons. First, you have only a few registers to work with. Second, you have to be careful to remember where your variables are. And third, you have to be careful that the side effects of some operation don't wipe out one of your values.